Okay, in this video, I'm going to demonstrate the use of Stata in order to carry out path analysis. And the basic path model that we are going to be working from is this one right here. I've gone ahead and drawn this into the graphical user interface in the program. And basically what we have are measures of students' mastery goal orientation, performance goals, level of interest in their subject matter, anxiety, and then a measure of academic achievement. Now, what we're going to do is start by essentially importing the data into the program. So I'm just going to go to File, Open, and I'm going to pull in this data set right here with complete data. And so you can see that we have our measures of performance goals, achievement, mastery, interest, and anxiety that are evident right there. And we'll just take a quick look at the data set, just go under the data editor, and so you can see that we have each of our variables reflected in each of the columns within our data set. So to essentially draw our model, what we're going to use is the graphical user interface. So we'll go to Statistics, go to SEM, and go to Model Building and Estimation. So you'll notice that the default on my computer is set up at a pretty large setting in terms of zoomed in. I'm going to set it a little bit lower, down to 150, and you can see the drawing space gets a little smaller for us. So I'm going to use these icons to draw the basic model. So I'm going to click on Add Observed Variable, and it's a button. So as long as that button is clicked, I can basically set up, go through and click all of these to get my manifest variable boxes drawn. Now I'm going to click off of that, so essentially click the button off, and now I can go to each box and use a little drop down here to identify the variable for where it belongs. So there's performance goals here, we have interest here, we have anxiety here, and over here we've got the achieve variable. Now to draw the effects, the direct effects in the model, I'm going to go to this button right here where it says Add Path. And so as I add the paths in, you can see it's in green. And once I click off, you can see that now we have error terms that are drawn in. Another term for it is a disturbance term. So as you can see, as we add arrows from one variable to another, the errors fill in automatically, and so we don't have to do this kind of manually like you might have to do it in Amos. So at any rate, there you go. Now, at this point, you'll notice that mastery and performance goals do not have error terms associated with them. But I may want to incorporate a covariance between these two variables. So to do that, I'm going to click on this little button here for Add Covariance and just kind of draw from one to the other, and there you go. Also, I can kind of, I can kind of move some of these parameters around if I want to and kind of straighten it up. So there is that option as well. So you can see I can just move some of these variables around and clean it up in different ways. So at this point, what we're going to do is estimate the model. So to do this, we're going to go to Estimation, go to Estimate, and this box is going to come up, and you can see that the method is maximum likelihood. If we had missing data, we could use either maximum likelihood, which would essentially perform a listwise deletion before estimating the parameters, or we could use maximum likelihood with missing values, and that's essentially a full information maximum likelihood estimation. Which is probably a little bit more preferable than the standard maximum likelihood approach where we use listwise deletion. So we have a complete data set for this example, so we're going to stick with maximum likelihood. You'll notice that under this little tab here for standard errors, we have different options for estimating the standard errors. If it were the case that our data set exhibited significant multivariate non-normality, then I might be inclined to utilize the Satora-Bentler estimator instead of using the standard default standard errors. But we're going to stick with this for the purposes of the current demonstration. So next, we'll click on OK. And you can see that the model is estimated, and right now there's kind of a blank open space over here, but if you click on any given parameter, you'll notice that you get the unstandardized coefficient and the standardized coefficient. So you can see there's the B for this path right here running from mastery to interest. So that's the unstandardized coefficient, the standardized coefficient. We have the standard errors, the z-values, we have the p-values for those estimates, as well as the 95% confidence interval for both of those. So we can see in our model that that mastery appears to be a significant positive predictor of interest. You'll notice right here the p-value, it says 1.49 e negative or minus 19. That's just basically scientific notation, meaning that's a very, very small number. So you can pretty much interpret that as a p-value less than 0.001. If I want to go to the actual output screen right here, here it is. And so all those estimates and the standard errors, z-values, p-values, all those are presented in this particular particular box. So next, let's say I want to look at the overall goodness of fit of the model. So to do that, I can go to Statistics and go to the Post Estimation command box and go to Specification, Diagnostic, and Goodness of Fit Analysis and click on Overall Goodness of Fit. So you can see it says Goodness of Fit Statistics, GOF. Typically, if I'm going this route, I'm just going to go ahead and click on all of the above and then on OK. And so now you can see that we get our goodness of fit statistics. So you can see that we have the likelihood ratio chi-square test. Basically, this is our chi-square value and p-value. And we also have the RMSEA right here. A 90% confidence interval for that if we want to look at that, and a p-test for close fit down here. We also have CFI and TLI noted right here, and then the standardized root mean squared residual, which is right here. So basically, in terms of evaluating the fit, what we're looking for are a chi-square test that's non-significant. Now, and that would be an indicator of good fit. Just keep in mind that the chi-square goodness of fit test is really is probably de-emphasized more nowadays, given that the recognition that SEM is a large sample technique, and a lot of times you can have a minor lack of fit, but then that be considered statistically significant. Just because by virtue of the sample size. So other indices are the more descriptive types, like the RMSEA. What you're looking for are values that up to about 0.08. Values that fall between essentially 0.05 and 0.08 would be considered acceptable. Values closer to 0, 0.05 or less, would be considered really indicative of closer fit. We also have the CFI and TLI, and values that are in the 0.9s or above would be considered indicative of good fit. Optimally, that would fall around 0.95 or above. And then the SRMR, basically what we're looking for are values that are less than 0.05. And so you can see overall it looks like our model is not doing a particularly good job of fitting the data. We can also ask for equation level goodness of fit. So in other words, obtain the R-square values just by clicking on this button right here. And when we click on OK, you can see that we get the R-square values for each of our endogenous variables within the model. So the interest variable, you can see that we get the R-square is 0.36. In the model, there was only one predictor of interest, which was mastery goals. So mastery is accounting for almost 37% of the variation. Achieve was being predicted by, there was a direct effect for mastery and also direct effects of interest and anxiety. So the combined effect was approximately 38% of the variance in achievement was accounted for by the combined effect of those variables. And then anxiety was just predicted by performance goals, and so we're accounting for about 4% of the variation there. We can also ask for tests of direct, indirect, and total effects. Really quickly, just keep in mind that we actually already have the direct effects. If you go to the our table up here, all of these coefficients are reflecting direct effects within the model. A direct effect is just reflecting the arrow drawn from one variable to another variable. But we also have indirect effects where when we're talking about that, what we're talking about is the role of mediators in the model. So we could say that in this particular model right here, we've got mastery, and we're looking at its relationship to achievement. This path right here is a direct effect. This is a direct effect. This is a direct effect. But if we take this path right here, let's call it path A, and multiply it by path B right here, then that would be an indirect effect of mastery on achievement via the mediator interest. There's also a second indirect effect of mastery on achievement, which might be computed by multiplying path A, which is this path, times path C to anxiety, times path D to achieve. So there's actually two routes by which mastery is indirectly related to achieve. And when we run our analysis, the standard approach is to essentially kind of aggregate all of those indirect effects into a total indirect effect and get a significance value. So kind of going back to our presentation right here, the way that we can get some of that information is to go up to tests, contrasts, and comparisons of parameter estimates, and we can click on direct and indirect effects right here. And so let's do that. We'll click on that, and right here, and then just you can see that you've got a number of different options. You can ask for standardized effects and so forth. So I'm just going to click on OK, and so now you can see that we have our effects laid out. So in this particular case, we've got the command, by the way, is estat t effects, and we'll talk a little bit more about that later. But basically, you can see the direct effects. All of these coefficients right here are reflecting the paths within the model. So all of this information is essentially the same as before. You'll notice that this little coefficient for mastery is set to 0, and that's because there was no direct effect of mastery on anxiety that was specified. For the indirect effects, you can see that here there's no indirect effect of mastery on interest because there's only a direct effect that's specified between the two variables. So that's why this coefficient is 0 here. Then you can see predicting achievement. We've got interest predicting achievement. There is an indirect effect that's specified between interest and achievement, where basically we have interest that is predicting anxiety, and anxiety is predicting achievement. So there's an indirect effect being reflected here. So you've got the standard errors, the z-test, and the p-value for the z-test. So it's not statistically significant. Then when we look at mastery in relation to achieve, as I said before, there were actually two routes by which mastery has an indirect effect on achieve, and so when we sum those two routes together, we get this coefficient here. And you can see that the total indirect effect of mastery on achievement is statistically significant. When we look at performance goals and its relation to achievement, there's only an indirect effect that's specified between performance goals and anxiety, and that's, or excuse me, performance goals and achievement. So, and basically that occurs via anxiety. So there you go. So at any rate, then if you want to look a little bit further in terms of the total effects, we can look at those, and that's just basically summing up the indirect and total effects between any of the any two variables within the model. So that's essentially utilizing the post estimation commands right there. Also, if you want modification indices, you can click on that, and that's how you can get this information. The modification indices are just kind of an empirically based strategy for deciding on whether to add certain parameters within the model. The basic idea is if there would be a significant improvement in fit or by adding in additional parameters, then that might suggest that the need to add something in. But you want to be really careful with these and not start adding in parameters just in order to improve fit without having a reasonable theoretical rationale in mind. So this was the basic path analysis. There is another way that we could run the same path analysis, and that is by using syntax or using the command language. So if I go down to the command line, I can run the same analysis. I can type in SEM, and then inside parenthesis, I can lay out my relationships. So what I'm going to do is I'm going to type in mastery, and then basically a hyphen and a greater than sign, which is obviously providing an arrow, and then I'm going to type in interest. So this is specifying a direct effect between mastery and the interest variable. So next, I'm going to type in start another parenthesis, and instead of typing the names, I can actually just go up here and click. I can click on performance goals, and I can also click on mastery, and use both of those on the left side of the arrow, and those are going to be predicting the anxiety variable. So or actually we'll just do performance goals was going to predict performance goals was just going to predict anxiety. So I'll type anxiety right here, and actually one other thing, we'll add in the interest. That was the other part of it, because interest was also predicting anxiety as well. So now we've specified essentially, kind of going back here, we've specified anxiety being predicted by performance goals and interest. We've got interest being predicted by mastery, and now we're going to have achieve being predicted by interest, by anxiety, and by mastery. So I'm going to go here, and the next one we're going to say essentially mastery. We're going to use the interest and anxiety, and then we're going to draw in our arrow, and then use achieve down here, and there you go. So now we've drawn that in. We still haven't specified the covariance between the mastery goals and performance goals. So I'm going to type a comma here, and then COV, and then I'm going to use, and then I'm just going to click on performance goals and mastery here, and then round it out. So there you go. So at this point, I can hit enter, and I get everything that I just had before. And then if I want to use syntax in order to generate the overall goodness of fit statistics, I can type in estat GOF, then stat, comma, stats, and then all, and that gets us what we had generated before using the post estimation command. Then I can type in estat EQ GOF, and that will get me the equation level goodness of fit. And then I can type in estat and then TEFFECTS TFX, and enter, and there you go. You'll notice that when you actually draw out the model and run it, you can also see that, kind of going back to where we started, it actually generates the syntax for you. So you can kind of learn as you're going along just by using the drawing program. Okay, so that's kind of a demonstration using the standard approach to estimation. Now let's try let's take a quick look at what happens when we have missing data. So I'm going to go to File, Open, and go to Path Analysis with the incomplete data. This is a Stata file. I'm going to click on Open here, and now we've got our basic model, and I'm just going to rerun from this using the standard maximum likelihood. And so remember that we had 140 cases in our data set, and so for this particular demonstration, by the way, looking at the data, you'll notice, let me kind of click off of this for a second. When we go to our data and look at the data editor, you'll notice that we have blank cells reflecting missing values on some of the variables. So let's see what happens when we run our analysis this way. So I'm going to go to Estimate Maximum Likelihood, click on OK, And so now we have our coefficients and so forth. And let's look at our output. You'll notice that now the number of observations is 132, and that's essentially reflecting the fact that listwise deletion was utilized in estimating the parameters within the model. Just keep in mind that one of the big downsides of listwise deletion is that um, that essentially your sample size can drop dramatically if you have a large number of missing data, and particularly if it's distributed over a number of variables that are included in your model. So at any rate, let's now look at the full information maximum likelihood estimation. So I'm going to go here to estimate and click on maximum likelihood with missing values, and then click on OK. So now when I look at the output here, you can see the number of observations is 140, and basically the estimation method is MLMV, which is indicating the full information maximum likelihood estimation. And what it's doing is it's maximizing really the information that is available in the data that we have. And so we have estimates in the same way that we had before. So these are the model parameters, the standard errors, t-values. These are all the direct effects. We can still ask for estat, GOF, and then stats all in parentheses there. And you'll notice that we get all the same types of information. There's our chi-square test, RMSEA, CFI, and TLI. You'll notice down here it says SRMR is not reported because of missing values. So we don't get that piece of information that we had before. We can also say estat, GOF, or EQ, GOF, and there's our equation level goodness of fit. And then we can say estat, T effects, and then hit enter, and there you go. So we have all of that information as we had before. If we let's see if there was anything else I wanted to mention in this video. I think that is actually going to round it out for this particular video. Just note that if we use the same syntax that we had before and we were running our basic model, if we added in the line of as a method for MLMV, then that would actually generate a full information maximum likelihood estimation solution. So I don't really want to spend time redrawing it out down here, but yes, you could certainly use syntax to or the command language to generate that model. So that pretty well concludes this particular demonstration, and I hope you find this useful.